Thank you, Scott. Okay. I'm Daryl Gotham. Let's see. So Scott had mentioned the Great Lakes Environmental Infrastructure Center. We here at, as I call it, GLIAC, are part of the Environmental Finance Center Network, which is a group of university and nonprofit-based organizations that work together to provide this type of training. And we do that typically through grants from EPA. So the Environmental Finance Center Network is established such that it covers each one of the 10 EPA regions. And as you can see, we are located in the Great Lakes region. We are in the Upper Peninsula of Michigan. So we cover those 5 EPA region states. We also are, this training today that we're providing was based on a request from the state of Massachusetts, but we cover typically Indiana, Illinois, Michigan, Minnesota, Ohio, and Wisconsin, along with the American Indian governments in those areas. There's some information on our contact stuff. So let's get on to the presentation. What we're going to cover today, we'll cover surface water sources for surface water treatment. We'll get into some basic math that's helpful when it comes to surface water treatment. Greg will cover in a little more detail coagulation, flocculation, sedimentation, and filtration, some of the important processes involved with surface water treatment. So surface water sources typically include rivers and lakes and streams. Any place that has sufficient amount of surface water, I'm sure if there's a community nearby, has been considered as a source. There are some qualities that go along with surface water that are different than we would typically see with groundwater. Those are, we end up with a lot of solids in there, so there's high suspended solids. We have exposure to the air, and different things. So we're going to have some microbes. So we'll have microbial contamination. The water quality is going to vary quite a bit. It can vary between sources, and in the actual source itself can vary quite a bit. Itself based off of things like rainfall and how we're using the land around the surface water body. And then it's subject to extreme changes in flow rates and water levels. I think of the floods in Texas, and we can see how quickly a river can increase in flow and height. The same type of thing we're seeing in the Great Lakes is we're seeing some low water conditions in the Great Lakes, which they tend to be cyclical. Human activity obviously can have a factor on that as well. So there's a lot of different places that we have concerns about contamination entering our surface water watersheds. Watersheds for surface water are similar to the wellhead protection areas that groundwater systems have. So we want to protect those areas, and we can look at all these. There's several different things from failed septic systems, the nutrients that can enter from that, the pathogens that can enter. We've got coastal development, impervious surfaces. So how the coast of in this case, a lake might be developed can affect the quality of that or the contamination that might enter. We can have sedimentation and toxins, stormwater runoff from municipalities, towns, villages, things of that nature. There's several different things that come into play with that. Agriculture potentially adds nutrients from, could be from chemicals added, could be from farms that have animals on it. Sedimentation is a concern anytime we We do things that upsets the natural vegetation, deforestation, road construction, agriculture, all of those have the potential to do that. So the contaminant sources that potentially impact surface water quality are typically in three different categories. We have point source pollution, and those are the things that we can identify pretty easily. We know there's for instance, a wastewater treatment plant, and that discharges at a certain point. Usually they'll go into surface water bodies of some sort. And so we know where those are located, and we can identify them. And the same thing could be for an industrial plant that has a discharge as well. The remainder of the remainder of the discharges like that are not as easy to identify, and we call those non-point source pollution. So it's convenient. The ones we know of, we call point source, and pretty much everything else we call non-point source. And those are quite often associated with the stormwater runoffs from communities, any agricultural, if it's off of farm fields, things like that. And then the third type we consider air deposition, and that can be either something falls out of the air and it lands on the ground, and then water runs across it and it ends up into the source water, or it can be something like back in the 80s and early 90s, we used to talk quite a bit about acid rain. And the idea behind that was there were particles in the air, and it rained, and those particles were taken up by the rain and then ended up on the ground and ultimately into surface water bodies. And just as an idea, the pH of acid rain typically ranges from 4 to 5 on average. So that's quite a bit different than what we would normally anticipate in a surface water body. So we've got lakes and reservoirs, but we also have rivers and streams, and rivers can be some of the most difficult sources for surface water to treat. They're considered very flashy. They have, the water levels can rise and lower. They can be easily impacted by runoff from different things. We look at this in this figure, we've got on the left-hand side, we've got some non-point sources. And on the right-hand side, we've got some point sources. And we also have, in the center, it shows, an oil tanker and the potential for oil spills. So rivers and streams can be difficult from a couple of aspects, like I said, because they change so quickly, and then also they're subject to so many different things. If there's a release that's upstream of our community, that will come downstream, and we have to be prepared to deal with that. So, and then lakes and reservoirs, they have their own. Typically, they're a little more stable. They're used more often as a surface water source, but they have their own issues. Lake turnover can be a concern in the spring and the fall, and that's mainly due to the fact that we've got in a lake, typically the colder water will be at the bottom and the warmer water at the top. And in the spring and in the fall, we have the potential for that water to turn over. We end up with cooler water on top, which wants to sink down to the bottom, and then that water on the bottom, the warmer water will then go to the top. What this does is it upsets the balance. It causes stirring of the sediments that are on the bottom of the lake, and they end up coming up to the top, and those can be brought into our treatment plant and cause some issues, elevated turbidity, things like that. The other concern that we have with lakes and reservoirs is the potential for eutrophication. eutrophication. And that's where you get nutrients that run off into the lake or reservoir, and those nutrients cause the algae and plants to, I mean, they love that, so they're gonna take that up, and they're gonna prosper in that water body. And so that can cause problems. When the algae dies off, it has the potential to cause fish kills, and we typically see a reduction in the quality of the water. Algae blooms can also cause problems when they die, and they release compounds that cause taste and odor concerns. So this is something that has been experienced quite a bit in the Great Lakes, specifically with Lake Erie, where we have these harmful algal blooms that grow out of control. They die off, and it's also known as red tide in the marine or in the saltwater areas. So the Safe Drinking Water Act has what we call a multi-barrier approach to ensuring good water quality, and so that every aspect of the treatment cycle and delivery of the water to our customers, there's barriers that are put in place to keep the water quality up, to keep from having things that contaminate or decrease the water quality. So in surface water, we look at watershed management, and that's very similar to a well control area, or so we want to manage what goes on in the watershed so that we can keep from having contamination and sedimentation and things like that entering our surface water, so that we don't have to deal with treating those and potentially having those go on to our customers. So we want to identify the area where all of the water will come from, and then put in place management practices that ensure that it's maintained, and we're receiving quality water to our source. So as we see, we've got water sources. Surface water is subject to all these these runoff from across the ground and into our water body, and as such, we need to make sure that we filter and we disinfect. We want to make sure that we kill off any microorganisms that the water may have picked up as it traveled across the land, and any organics that it picks up. It has the potential for creating disinfection byproducts, which are problematic. We'll talk probably more about that here later, but when we add chlorine to certain organics, the result can be disinfection byproducts, and they have the potential to cause cancer. So EPA regulates those. So in this instance, we've got a cattle ranch. There's the potential that we're going to have contamination from that ranch that ends up getting into our surface water source. So this natural organic matter that comes off the ground and gets potentially into our surface water source it can lead to disinfection byproducts, but it can also contribute to the growth of biofilms out in the distribution system and in our pipes and our plumbing, and those biofilms have the ability to harbor harmful bacteria. So we want to limit how much natural organic matter is getting out, and also to limit because that'll help limit the amount of biofilm growth that we get. And they can harbor pathogens, the biofilm. That can cause some compliance issues, and they can affect how our infrastructure operates. Now, if we have optimal surface water treatment, we should be able to remove most of that organic matter and limit how much biofilm growth is occurring. Oops. So why do we treat surface water? Why can't we just pump it out of the ground like we do groundwater? And we've talked about some of these things. Our sources, they're likely to contain microbiological pathogens. Bacteria, protozoa, viruses are more likely to be in those than they would be in a groundwater source, and they can cause serious illness or possibly even death. We also have the possibility of picking up some other things as the water is either traveling across the ground or through the ground, or as it's in the surface water source. Those are potential for inorganics, organics, and radiological components. So the whole idea is that the water treatment is going to remove those contaminants so that we can ensure that we're providing safe drinking water to the public. There's several different kinds of contaminants that we can find in surface water. As you look at these photos, the one on the left, it looks like we've got a bit of runoff from a field, potentially some erosion. So we can pick up defined particles such as silt, clay, and sand through erosion, construction sites. Quite often, construction sites have the black plastic around them, fenced in to keep all that erosion from going off site. The photo in the center appears to be, it looks as if we've got some erosion happening, possibly next to a farm field with a fencing here. So that could be a case where not only are we getting our erosion of soil erosion, but we're also getting potential for animal waste flowing across and into our water body. And then the third one shows just some of the algae growth, the plants, things like that in a surface water source that could also cause some issues. I mean, we have natural organic matter in that. And then other potential contaminants, as we see the figure on the far left has what it looks to be an industrial area. We've got quite a bit of impervious pavement, it looks like, with some sort of equipment on it. We've got several things along the shoreline. And then it appears as if there's a plume or plumes that are coming off from the site. So that's all the potential to cause some contamination to enter the surface water body. In the center, this may not be a discharge from a wastewater treatment plant, but there's always the potential that either untreated, partially treated sewage, through different mechanisms could get into our water body. So we have to be aware of and concerned with that. And then, we just all the microorganisms, the different things that the bacteria, the protozoa, the viruses, the parasites that potentially enter through our surface water. And we also have the potential for some chemical stuff. That's always a concern when we really don't have control of everything that goes into our surface water. There's also microplastics is a common theme nowadays, as well as personal care products, both pharmaceuticals that could be from drugs that we have prescriptions for or we don't, herbicides, pesticides, PFAS, the forever chemicals are now have now become a major concern in this for our surface water. So now we will go on to our first poll. And poll number 1, thank you for putting that up, Scott. What is an example of an impact of non-point source pollution? A, wastewater effluent discharges add TSS, total suspended solids, to a stream. B, precipitation causing water to flow into rivers, lakes, and streams. C, nutrients from agricultural runoff leads to eutrophication in lakes and rivers. Or D, all of the above. So we'll follow and see when we get a good number of responses, then we'll let you all know what the correct answer is. We're up 77% of people responded. Give a little bit more opportunity here. All right, I'm going to end the poll and share the results. So it looks like we have the top response was at 36% was nutrients from agricultural runoff leads to eutrophication in lakes and reservoirs. Pretty close here. We've got all of the above at 32%. Precipitation causes water to flow into rivers, lakes, and streams at 29%, and wastewater effluent discharges add TSS to a stream. So, all righty. So let's move on. Let's see what the correct answer is. So the correct answer is nutrients from agricultural runoff leads to eutrophication in lakes and rivers. And so yes, it does. That is an impact. I think the key thing to this is what's an impact. If our wastewater effluent discharging to a stream is a point source, it's not a non-point source, so that wouldn't be the answer. And then precipitation causing water to flow into rivers, lakes, and streams it's not necessarily an impact, because just because it flows into it doesn't mean that it's going to impact the river. So non-point sources include general runoff from agriculture operations and stormwater that can bring nutrients into water bodies, increasing the growth of algae, which can affect our water quality. So as I said before, the Safe Drinking Water Act uses a multi-barrier approach. So we're going to take and have several different things throughout the from source to out into the distribution system that we're gonna hopefully keep from having water quality issues and allow us to have good quality water. And the first we talked about already is source water protection, watershed management. And then we'll look at the water treatment processes, coagulation and flocculation, sedimentation, filtration, disinfection. Water quality testing will also can also be a barrier to bad quality water or microbes getting into the water. And And then how we manage our distribution system will also, with water age and pressure, having a good cross-connection control program, our disinfection and how we meet our compliance monitoring. These all are barriers, are part of this multi-barrier approach. So, so now we're going to briefly look at the water treatment processes. So for surface water treatment, there's two main types of treatment that are involved. We've got conventional treatment, which we're looking at on this slide. And so conventional treatment is where we take our raw water, we add a coagulant. So that what that does is the coagulant sticks to the particles that are suspended in the water and it makes them sticky. So these these particles are sticky. We put that coagulant into a flocculation basin, and we stir that up, and that causes those sticky particles to come together, and they make bigger particles. And our next step is sedimentation, and with sedimentation, we're going to widen out, slow our flow down, so that those particles they're going really slow and they just kind of settle out. So they're going to drop to the bottom. And so the idea is we've taken something where we've got all these particles, we've made them stick together, they get heavy, we've slowed down the flow, and most of them drop out. And then the final thing that we do is our filtration. And so as far as I would say final, we'll also do disinfection, but this is the last step where we're looking to take particles out. And so we put that through some media, could be all sorts of different types. We could have several different types. And the idea is that the spaces between these particles are small enough that it pulls the floc out. Anything that escapes through sedimentation gets removed through filtration. So direct filtration is pretty much the same thing, but you'll note that there's a part missing. So we put our raw water in, we add a coagulant, we go through coagulation, we go through flocculation, but we're missing that step right there for sedimentation. So usually in the case of direct filtration, we're looking at a really low turbidity water, something that's probably a little higher quality water, so it requires a little less treatment. So that saves us that sedimentation step, which, if you've got a plant that doesn't have a lot of room, sedimentation basins can take up a lot of space. So then it just goes through our filtration, disinfection, and off to treatment. Okay, so next I'm going to cover some basic math stuff that goes along with surface water treatment. So we'll look at areas, volumes, doing some conversions of flow. We'll talk about concentration and dosage. So we're going to look at two different formulas for area. In this case, we'll look at rectangular areas. That's important because a lot of our basins will be rectangular. And so these are commonly used for filtration and sedimentation basins. So we need to know how to do calculations for those. So in our example here, we have a rapid sand filter with a width of 10 feet and a length of 20 feet. Width of 10 feet, length of 20 feet. What is the area of the filter in square feet? So we simply take the area is equal to the length times the width. So the length is 20, the width is 10, 20 feet times 10 feet equals 200 square feet. Now, the other that we're going to look at is circular area. And this is important because, we will often have circular tanks. They could be storage tanks. In this case, in this example, we're gonna look at a circular sedimentation basin that has a diameter of 60 feet and the surface area. What is the surface area in square feet? So I know I learned area is equal to pi r squared. We can use that formula. We can also use one that is becoming more common now. It's the area is equal to 0.785 times the diameter squared. If you look, if we put in for area is equal to pi r squared, the area is equal to 3.14 times the radius, which is 30 feet, times the radius again. And that gives us 2,826 square feet. If we use the area is equal to 0.785 times the diameter squared, we're going to take that 0.785, multiply it by the diameter, and the diameter again, and lo and behold, we get the same answer. So at this point, it's a personal preference that you use the formula you like, but we can look down here, and if we take pi r squared, which is 3.14 times the radius is equal to the diameter divided by 2. So we multiply that out, and what we're going to end up with is 3.14 times a quarter. That's a half times a half is a quarter, times the diameter squared. So that basically tells us that that 0.785 is a quarter of pi. And that's why this formula works. So you'll note that there's some formulas and some conversion factors and things like that I'll talk about. Just so you know, a heads up, you may want to jot these down when it comes to doing the poll. We want to make sure that you have the information you need. So if it's a formula you're not familiar with, write it down. You'll have it available for when time comes to do the poll. Another thing that we need to do are conversions, whether they're between areas or lengths. Quite often we'll go back and forth between feet and inches. If you were working in the metric system, there's potentially conversions as well. But if we look at this figure on the left, we know that foot is equal to 12 inches, while a square foot is going to be equal to 144 square inches. So because it's 12 inches times 12 inches, 12 times 12 is 144. So for our problem, our conversion problem, we have a rectangular surface measuring 60 inches by 72 inches. What is the area in square feet? So we can go about this, in two different ways. It's up to you how you do it. We're going to show both methods. In the first method, we're going to convert everything over to inches, or we're going to take things in inches, first of all, and then we're going to figure it out, and then we can convert it into square feet. In this case, the area is equal to the length times the width, 60 inches times 72 inches, total of 4,320 square inches. But if we want that in square feet, we need to do a conversion. So we're gonna take and divide our 4,320 square inches by 144 square inches per square foot, and that gives us our 30 feet or 30 square feet for our for a container here. So the other method would be that you would convert the measurements from inches to feet right from the get-go. So we know there's 60 inches and there's 12 inches in a foot. That means that 60 inches is equal to 5 feet, and 72 divided by 12 gives us 6 feet. So the same rectangle is equivalent to 5 by 6. We can take then and multiply them together, length times width. 5 times 6 gives us 30 square feet. So it's up to you, whichever way you like. You can go either direction. So here's another important volume conversion. So 1 cubic foot, so a container, say that was 1 foot by 1 foot by 1 foot. If we were to fill that up, it would be almost 7.5 gallons, 7.48 gallons. So this is something this would be a factor that you would want to remember or write down. It's an important conversion when it comes to working with surface water treatment. So how many gallons can a 24 cubic foot tank hold? So if we know that there's 7.48 gallons in 1 cubic foot, how many will 24 handle? So we look here and we multiply the 24 cubic feet by our conversion factor, 7.48 gallons per cubic feet. The blue cubic feet are going to cancel out, and that's going to give us an answer that's just in gallons. 179.5 gallons. So that is nearly 180 gallons in a 24-foot cubic tank. So let's look at volume of a rectangle. These basins have a depth to them as well. So we can figure out the surface area, but we also need to know depth in order to get the volume. And that formula is for volume of a rectangle is length times width times height. And we're talking about cubic feet in that instance. So if we have a rectangular sedimentation basin that it's got a depth of 10 feet, a length of 50 feet, and a width of 20 feet, what's the volume? And we want that answer in both cubic feet and in gallons. So if we look at our volume, we've got 50 feet by 20 feet by 10 feet. That gives us 10,000 cubic feet. So we've answered part of our question, but we now need to do that conversion where we go from cubic feet to gallons. So if we take our 10,000 cubic feet, we multiply it by 7.48 gallons per cubic feet. Our cubic feet cancel out, and our answer is going to be in gallons. And that is equal to 74,800 gallons. So we determine the volume of a rectangle. Now let's look at the volume of a cylinder. So the formula for volume of the cylinder, we can go with the 0.785 times the diameter, and that's just times the height. So that formula, or you can take the volume is equal to pi r squared times the height. Once again, it's up to you which one you prefer. So if we've got a tank with a diameter of 20 feet and we've got a height of 30 feet, what's the volume? So we take our volume equal to 0.785 times the diameter of 20 feet times 20 feet times the height of 30 feet. And that gives us 9,420 cubic feet. So what if we wanted to know how many gallons are in that? So we just take our 7.48 gallons per cubic foot conversion factor. Note that the feet cancel out. It's just going to give us gallons. So if we multiply 9,420 by 7.48, we get 70,461.6 gallons. So our next thing up is our next pole. So in pole number 2, we have a cylindrical storage tank with a diameter of 24 feet, and it's filled to a height of 20 feet. How many gallons are in the tank? A, 9,600 gallons, B, 11,520 gallons, C, 67,643 gallons, and D, 86,170 gallons. Scott, can you set a 3-minute timer? Give 3 minutes for this. All right, we've got a good deal of our responses in. And timer's up. Share the results. We had 86%, say C, 67,643 gallons, 8% for B, 3% for A, and 2% for D. Let's look at our let's look at the poll and work or the problem and work it through. So if we take our 0.785 times the diameter, times the height, and then we're going to multiply that by 7.48 gallons per cubic feet to get it into gallons. We're just jumping ahead, doing them all at once. You throw those numbers in there. Note that the cubic feet, divided by cubic feet cancel. And I believe it was answer C, 67,643 gallons is the proper answer. So our next topic is going to be flow rate. Quite often we need to know what the flow rate is, and we may need to manipulate the flow rate to give us other information. So in this case, we have a pump that fills a 5,000 gallon tank in 12 minutes. What is the pump output in gallons per minute? So we take our 5,000 gallons, we divide it by the 12 minutes that it takes, and that gives us 416.7 gallons per minute. That's how much, that's the flow rate of that pump. So now if that pump flowed for a full day, how much would it pump? So if we take our 416.7 gallons a minute, we multiply it by 60 minutes an hour, and then we multiply that by 24 hours in a day, we're going to cancel out our minutes, we're going to cancel out our hours, and we're going to be left with a number that is in gallons per day. That's what we want, right? How many gallons in an entire day? So we multiply that out and we get just over 600,000 gallons in a day. So some people like to take and jump and consolidate this all into this conversion of time into one. And if you like that, you can do it by multiplying the 24 hours by 60 minutes per hour, which will give us the number of minutes in a day. And that's 1,440 minutes in a day. And if you so choose, you can choose to remember that conversion, or you can go through and just calculate it out each time. Now, at times we're going to need to adjust our flow rate from gallons per minute to million gallons per day. And so here's the factor that we have to do that. We take our gallons per minute, we multiply it by the number of minutes in a day we just calculated, and we divide that by 1,000,000 gallons over this million gallon symbol. So when we do that, let's see, we'll look at a problem to help us get that work through this. We have a pump that produces 400 gallons a minute. What is the flow in million gallons per day? So we take our 400 gallons a minute, we multiply by our minute to day conversion. We divide that by the million gallons per million gallon. And that gives us 0.576 million gallons a day. Now, we're going to go on and we'll talk about flow. So flow is noted as Q, and flow is equal to the area multiplied by the velocity of the flow. So their units, flow, are in cubic feet per second, or CFS. The area is in square feet. Our velocity is in feet per second. And look at where the cross-sectional area of a pipe flow is circular. So let's work a flow problem. So Q equals area times velocity. Water is moving through a 6-inch pipe at a velocity of 2 feet per second. What is the flow in cubic feet per second? So our first step, we want to convert from inches to feet. So we need to work with the same units. So we want to convert from inches to feet. We do that, our 6-inch pipe divided by 12 inches. So we all know that a 6-inch pipe is a 0.5 foot or a half foot pipe. Next, we calculate the area. So what's the area of the pipe? So area we know is equal to 0.785 times the diameter, which we already determined to be 0.5 feet, times the diameter again. And that gives us 0.19625 square feet. So that's the area of our pipe. Now we know that our velocity is 2 feet per second. So our flow is taking the area that we calculated here, multiplying it by the velocity. And we do this, note that one of the 2 feet here is going to cancel out with this one here. Or no, they're gonna multiply together, my mistake, to give us in cubic feet per second, or CFS. All right, so we've worked through some problems in cubic feet per second and gallons per minute, but we may have the need to go back and forth. We might be given something in cubic feet per second, we want it in gallons per minute, and vice versa. So if we're going to take and go from cubic feet per second, we need to get rid of our seconds to get to minutes, because we had seconds, we need minutes, and we're going to have to convert from cubic feet to gallons. So this is our conversion that does that. So that's what we do for that. Now, if we need to go in the other direction, we're going to start with gallons per minute. We need to get rid of the minutes and get to seconds. And then we have to have our conversion to go from cubic feet to gallons, or from gallons to cubic feet. So let's look at these flow rate conversions, and we'll do a problem. So we have a pipe that has a flow of a half a cubic feet per second. What is the flow in gallons per minute? So we're starting with cubic feet per second. We need to get to gallons per minute. So we're going to use this top conversion. Put our half a feet per second, half a cubic feet per second, multiply it by 60 seconds per minute to get rid of the seconds. Multiply it by 7.48 gallons per cubic feet to get rid of cubic feet. And our answer is 224.4 gallons per minute. So now, if we have a pipe flow of 500 gallons per minute, we want to know what it is in CFS, we're going to enter our numbers into the conversion here. So we'll take our 500 gallons per minute, multiply by a minute per 60 seconds, and then multiply it by 1 cubic foot per 7.48 gallons. And we'll have an answer that's in cubic feet, 1.11 cubic feet per second. So for concentration, quite often we'll have to do things, we have to look at things in parts per million, and parts per million is basically 1 part of something per a million parts of the rest. Milligrams per liter is the same as parts per million. It seems a little bit confusing, but they are technically the same. And milligrams per meter is the weight of solids in milligrams that are in a 1 liter sample. So it's weight per volume, but a liter of water weighs 1,000,000 milligrams. So it works out to the same. It's parts per million is the same as milligrams per liter. And then percent, it's parts per 100. And then another thing to keep in mind, that 1 over 100 is expressed as 0.01. 1 over 100 would be 1% as well. So now let's look at the pounds formula. So the pounds formula is the flow multiplied by the concentration. So 1,000,000 gallons per day multiplied by concentration in parts per million or milligrams per liter, multiplied by the weight of water, which is 8.34 pounds per gallon. And that'll give us the feed rate of the chemical in pounds per day. So in our example, we have a well that produces a flow of 600 gallons per minute, and the chlorine dose that we're looking for is 1.5 milligrams per liter, or parts per million. What is the feed rate for gas chlorine in pounds per day? So we're going to have to convert our flow from gallons per minute to milligrams per day, or million gallons per day. We've done that already. That's taking our 600 gallons per minute, multiplying by the number of minutes in a day, and then dividing by our 1,000,000 gallons per million gallon. So we crunch the numbers, the gallons cancel, the minutes cancel. We're left with 1,000,000 gallons per day. and that's 0.864 million gallons a day. Now we're going to use the pounds formula. So we're going to take our million gallons a day, we're going to put it in as our flow. We'll take our concentration of 1.5 million milligrams per liter or parts per million, and then we're going to multiply that by the weight of water of 8.34 pounds per gallon. So we do that and we end up with 10.8 pounds per day. These are all important things when it comes to surface water treatment. So let's just do another problem here. A water well flows at 1.2 million gallons a day and has gas chlorine dosed at 2 parts per million. What is the feed rate in pounds per day? We take our pounds formula, 1.2 million gallons a day. We multiply by our concentration of 2 milligrams per liter times the weight of water at 8.34 pounds per gallon, and we get 20 pounds per day. So we can rewrite the formula as 1,200,000 gallons times 2 parts of chlorine per million parts times 8.34 pounds per gallon. So what is 1,200 gallons of water weigh? We take our gallons, we multiply by 8.34 pounds per gallon. That tells us that we have just over 10 million pounds of water in 1.2 million gallons. So if we have just over 10 million pounds of water in a day, and there's 2 parts of chlorine, we know that we have 20 pounds per day of chlorine. This just helps to show the concentration of the pounds formula. It expresses the weight of chemicals as a portion of the weight of the water. In this case, chlorine weighs 2 per 1 million times the water weight. So then we have our final poll. A groundwater well produces a flow of 350 gallons per minute. Chlorine dose is 1.3 milligrams per liter. What is the feed rate of gas chlorine in pounds per day? Scott, can you set a 5-minute timer? We'll take our 5-minute break here, and at the end, we will. I'll finish this up, and Greg will take over with the remainder of the presentation. So. Oh, all right. Well, time is up. Let's see. We will. Hopefully, everybody had a chance to do the poll. I apologize if you didn't, but we're going to end the poll. And so the responses are 81% of the respondents said 5.46 pounds per day. And we had 11% at 4.65, 5% at 3.52, and 3% at 6.82. So shared the results just so everybody can see them. So then we'll close this out. Let's see. So we'll solve the problem. Groundwater well produces a flow of 350 gallons per minute. Chlorine dose is 1.3 milligrams per liter. What is the feed rate of gas chlorine in pounds per day? Are we seeing the?
Yeah.
Okay. So the first thing we're going to do is we're going to convert the flow to million gallons a day. And we do so by taking our 350 gallons per minute, multiplying by the number of minutes in a day, and then dividing by our million gallons per million gallon. We do that and we get 0.504 million gallons per day. The answer is C. And that's how we got the answer. Oh, sorry. No, sorry. We take our 0.504 million gallons per day. We multiply that by 1.3 milligrams per liter, which is our concentration, and multiply by the weight of water in pounds per gallons, and we get 5.46 pounds per day. Sorry, we had a little thing between Greg and I, who is operating the slides. Thanks for doing that, Greg. So now Greg will be taking over the second half of the presentation. Thank you all.
Thank you, Daryl. That was excellent. Is my audio coming through okay? And screen?
Yes.
Yeah, I was a little slow on the clicking there. Sorry, Daryl.
No, it was about me. I was looking at two different things. My bad.
Yeah, Daryl and I are switching off two different technologies here. We're in two different locations. And I looked at the chat, and thank you for all the hellos, and thank you for the personal hello, Daniel. I see we have some friends from Massachusetts and all over the country, Colorado, Oregon, Nevada, and a lot of our friends from Michigan and Nebraska even. And so thank you all for attending. I hope you're enjoying the training. That was an excellent introduction and math section that Daryl provided us. And like Daryl said before, we're going to get into a little more detail about the removal processes here: coagulation, flocculation, sedimentation, and then finally filtration. When we add coagulant chemical and mix that into the water, that is known as coagulation. But what is happening is that the negative charges of the particles in the water are being neutralized because our coagulant chemical is positively charged. And these particles in the water are small, but they're also repelling each other. They don't want to clump together. So the coagulant chemical, it neutralizes those charges so that we can begin to form floc. The particles can adhere to the coagulant particle and to each other and create larger and larger floc. We're trying to do that so we can get large enough particles to either settle out or be filtered. There is a basic problem with the size of particles here that I want to show you before we get into it. You notice the very small particles that are 1 micron all the way down to 1 nanometer. These are the 1 nanometer particles especially are suspended solids, but they're so very small, they're very difficult to be measured. You probably wouldn't be able to measure these in a suspended solids test. They would go right through the suspended solids filter, and we'd have to measure them as dissolved solids. That's one of the reasons we use turbidity. We'll talk about turbidity later on, but it's very difficult to measure these, but it's also difficult for them to settle out. you see a particle that is 1 micron in size, is about the size of a bacteria or a particle of algae. It would take 8 days to settle. That is relatively small compared to the 1 nanometer particle, which would take up to 200 years before it would settle. So these particles are so small they just don't want to settle, and part of that is because of the ratio between the surface area and the volume. As particles get smaller, their surface area compared to the volume is larger. All the larger particles, sand and gravel, even fine sand, and a lot of the protozoa and algae and clay particles will settle within about 2 hours. And so they will settle out without any treatment at all. But those small particles are what we're trying to work on. That's why we're adding coagulant chemical. The little note I added here, everywhere between about 1 micron um, and 1 nanometer, that's kind of where we find our colloidal particles. They're so small, they're hovering between dissolved and suspended. And to get an idea of the size here, a micron is 1,000th of a millimeter, and a nanometer is 1,000th of a micron. The next step down, when you get smaller than a nanometer, we're talking about angstroms, which is a unit they use to measure at the atomic level. So we're getting very small here. Now, typically, if we're measuring solids, we can do a couple different types of test. One is we could filter the water. You see that little unit on the lower right-hand side of your screen. That's a unit for passing water through a filter. There's a little vacuum pump that draws the water through into that a flask, and the suspended solids are filtered out, theoretically. And then to measure the dissolved solids, we would take that water that was filtered and evaporate it, and then weigh the remaining solids after the water is evaporated. Now that is not a complete adequate test for the particles that we're dealing with, because the water that passes through the filter, it would also contain some of those very small colloidal particles. So we'd have to measure those very small colloidal particles with the dissolved solids test. So a true dissolved particle is a substance that's broken down into its ions. It's become evenly dispersed in the water. And the colloidal particles that we're trying to deal with, they're too small to measure with one of these total suspended solids tests. And you'd actually have to measure them with a TDS test. And once again, that's why we use the concept of turbidity. In a TDS test, we're basically measuring, or a total dissolved solids test, we're measuring the dissolved solids, but we're also measuring those particles that made it through the filter, anything less than about 1 micron. And in general, dissolved particles are anything that's smaller than about 1 nanometer. So colloidal particles are anything between 1 and 1,000 nanometers, and they really can't be filtered out or settled in a sedimentation basin. And they contribute to the color or cloudiness of water, and they can contain pathogens like viruses and bacteria and protozoa. So you can see how that experimental setup would work. You filter the water to capture the total suspended solids, and you weigh them, and then you would know the milligrams per liter, and then you would take that filtered water and you would evaporate the water away and measure the weight of solids after the water was evaporated. There's a couple of links here. There was a nice document from the University of Georgia that goes through these solids testing procedures. You can look at that link and look at all of their laboratory tests. And there's also a TSS test video that you can check out if you're interested in knowing more about that. If you look at the relative size of particles compared to some of these items that we see on the screen here, you can see an atom. It's a tenth of a nanometer. So atom's pretty small. It's not something you'd be able to see under a regular microscope, but just a little bit bigger than that, we have a 1 nanometer particle, a carbon particle. And just a little bit bigger is DNA, 2 nanometers, protein, 10 nanometers. So you can see how all these things fall along the range of sizes, and virus and bacteria are also in this colloidal range. To move something here. Now, one of the reasons I mentioned before, the surface area to volume ratio is a big factor in why particles won't settle. If we look at a meter cube, a meter size cube, it's like 3 foot by 3 foot approximately. Its surface area to volume, if we take the surface area, 60,000 centimeters, compared to the volume of 1 million centimeters cubed, if we take the surface area divided by the volume, we see it's about 0.06. But as you get smaller and smaller, it's like a centimeter cube. It's 1 centimeter on each side. The surface area to volume is 6. You see, we're increasing. For a 1 millimeter cube, the surface area to volume is 60. And if we get all the way down to a 1 nanometer cube, the surface area to volume is 60 million. So that's like having a really large parachute where you have a large surface area and a very small volume, which means you don't have a whole lot of weight to drag that particle down to settle out. And it's not very large either. In addition, these particles, these small particles in the water are negatively charged and they're repelling each other. They don't want to come to clump together to grow larger particles. And I was curious about this, and I did some more research, and the negative charge in the particles has to do with the clays, the clay minerals that are in surface water, and which helps to impart the negative charges to the particles. If you want to know more about it, um, beyond what I know, you'd probably have to talk to someone like an organic chemist, which would be able to explain more. But I always wondered why wouldn't we come along and have some positively charged particles and have to use a different kind of coagulant? Um, and in some cases, in certain types of groundwater treatment, the contaminants are positively charged, and they do use negatively charged things like ion exchange. But in surface water, the particles are by far predominantly negative because of the clay uh, minerals that are in the surface water. So they're going to not only resist settling because of their small size and that surface area to volume ratio, but they're also repelling. That's why a positive coagulant that neutralizes these charges is so important. So basically the process is that we add coagulant chemical, which destabilizes the charges, and they begin to clump together to form microfloc. And we continue to mix and give them time to come in contact with each other. And eventually, when we get to the sedimentation basin, most of the particles are going to be large enough to settle. And here's a little image of some floc particles that have been formed in the water treatment process. The types of coagulants users, a bunch of different coagulation chemicals and polymers out there, but we'll look at some of the most common. And even though alum was used by the Egyptians, believe it or not, 3,000 years ago, they would collect water out of the river in big clay pots, then they would add some alum. It was it was not the refined form of alum that we use now, but it was the naturally occurring alum, and they would settle out the impurities in the drinking water. And we're still using it today. I believe it's still the most commonly used coagulant. And alum is aluminum sulfate, and you can see the Na2, that's sodium, and I might have something wrong here. A sodium and a sulfate here. There should be an aluminum molecule in there. I might have an error there. I'll check that out, and after we take a little break and see what's going on with that formula there. I think that should be an Al2SO4. Sorry about that. So basically what happens is alum goes into the water and it reacts with the naturally occurring alkalinity in the water to form aluminum hydroxide. So it has to use up alkalinity. Alkalinity must be present in the water to actually create flock. There's other forms too. Polyaluminum chloride called PaC. What they've done with that is they pre-hydrolyzed the alum. In other words, if alum needs OH, hydroxide ions, in order to form aluminum hydroxide flock, they already cause that to happen before it's even added to the water. So now when you add this PaC, you're not having to use up alkalinity from the water. It's already been done, and it can begin forming flock right away. So it affects the alkalinity and pH less. And there's an example of PaC. Ferric sulfate is a ferric-based or iron-based coagulant, and it's known to produce a denser flock. And it actually can produce flock that's too dense, which makes it difficult to handle. On the other hand, aluminum makes kind of a fluffy flock and a large amount of flock that results in a lot of sludge. Whereas ferric sulfate can make a denser sludge, so it can drop out faster, and it can operate across a wider range of pH. And so can ferric chloride. It can operate across a wide range of pHs, and it works well in cold water. That's why they use it. They used it in Flint, Michigan. They chose it because it worked well in cold water, and it promised to create very fast settling. However, it can also increase corrosivity. Ferric chloride is actually a waste product from metal turning metal iron ore into steel, and so it's also very inexpensive. And there's a ton of variations of coagulants out these days. So if you have a vendor that you work with, they probably offer you a wide range of custom chemicals, but these are the most common, the aluminum-based and the iron-based coagulants. There's different ways to feed chemicals. There's a couple methods to feed dry chemicals. Often coagulation is done with feeding liquid chemicals, but there are different types. There's volumetric and gravimetric feed mechanisms, which are used to feeding dry chemicals. And so the volumetric, they're calculating a volume using some kind of an auger or belt system where it's giving a certain volume over time. And they might have some kind of a vibrating mechanism to keep the chemicals from clumping up in the hopper. You can see a couple different types here. You can see the auger mechanism and the hopper. And it could potentially be used for coagulation. For example, dry powders of coagulant chemical, but that's not very common. It's more common for doing something like feeding lime or soda ash for pH adjustment, or adding powdered activated carbon, but often that's also fed as a liquid slurry. But these can be used. Gravimetric feeders, they calculate the amount that they're feeding based on a loss of weight, and they might be measuring the weight that's being carried on some kind of a conveyor belt, or looking at the weight loss in the hopper over time, and it'll continually readjust the speed of its feed based on the weight being lost. So it has to have a PLC controller to continually compare the water flow to the amount of chemical that's being fed. Most of the time we feed chemicals with some kind of a liquid feed pump, and you can see some different types here on the far left. Just a basic diaphragm pump. It has a piston diaphragm. And on the right-hand side of your screen, you can see the peristaltic pump, where it's basically a roller is pushing on a flexible piece of tubing, kind of like milking a cow. It's squeezing the liquid at a certain rate. So in the peristaltic pump, you would be uh, adjusting the speed at which that mechanism rotates to see how, to adjust how much chemical you're pushing in. And on the piston type pump, you'd be adjusting the length of the stroke and the number of times that the piston moves. And in this case, we're seeing a little rotating cam that's moving that piston, but most of the time we have a electromagnetic piston that is activating the piston and that pushes the chemical out. For mixing, there's a couple different types here. We have on the left of your screen here, we have an inline mechanical mixer. So the coagulant is being injected just upstream of a mixer. And so that vertical unit that's coming down to that pipe, it's a motor that's running a mixer. So the coagulant is injected, and then it goes through the mixer, and then it continues on to the coagulation basin. And here is a little bit different situation here, where there's a pump that's coming off of the pipe and being re-injected up downstream of the pipe flow. And as that water is going from the pump back to the pipe, there's the coagulant is injected, and it's pushing it upstream to cause some turbulence, to cause some mixing. That's called a pumped blender. A static mixer doesn't have any moving parts. The coagulant is injected, and it has to flow through a series of static mixing vanes that causes the water to change direction multiple times. Those are inline static mixers. And then just mechanical mixers, you would inject the chemical into a basin and use some kind of a mixing device. This would be the least efficient type of mixing because you have to deal with some of the corners and the outside areas of that mixing basin might not get as much mixing unless you're really careful to use baffling so you don't have dead spots, and you want to have a mechanical mixer that has enough shear force to give enough intensity to ensure you have complete mixing in that basin before it flows farther into the treatment chain. So with alum, there's a pH range that it works best in. And so we're going to use alum as kind of the focus of our conversation. And I want you also to think about times when we would not be able to use alum. And we'll talk about that next. But alum, it works best in this range of 4.4 to 6.0 pH. in general. And so you can see right away that most waters are probably going to have to be adjusted in the pH to make this work ideally. If you imagine most waters are probably around 7 pH, um, you know that you're going to have to adjust the pH down probably with some kind of acid like sulfuric acid. Now, for charge neutralization, there's two ways that alum is said to work. There's charge neutralization, and then there's sweep flocculation. And for charge neutralization, we have a lower pH in the lower range. Um, what is happening is the individual particles are being neutralized. And this is especially effective for very small particles of organic matter, like naturally occurring organic matter, and very small colloidal particles. So it's individually interacting with them, um, negating their charge and causing them to be able to form larger flock. Sweep flocculation actually can work above the 6.0 pH range, and basically it forms a gelatinous flock. There I have the aluminum hydroxide. I have the Al correct there. So it forms this flock of aluminum hydroxide, and it sweeps down through the water and it traps particles as it floats through. This is this is also effective, but not as effective in removing those color causing and disinfection byproduct causing particles of natural organic matter and things which cause color and taste and odor problems. Often we will shoot for a kind of a compromise pH, like say about a 5.8 or 5.9 pH, to take advantage of both of these forms of removal of alum. Here's a little diagram of the two ways that alum can work. You see charge neutralization on the left here, and here we have the aluminum hydroxide ions, those little positive charges there. They're reacting directly with the negatively charged particles to neutralize their charge. And so you get all these little particles that are ready to form flock. And that's primarily occurring below a pH of 6. And in sweep flocculation, we have this gelatinous aluminum hydroxide flock that sweeps down and captures those particles. To a certain extent, the effect is the same, but it's not going to be as effective with those particles that we really want to eliminate for optimized treatment. So it's capturing the flock as it settles down through the water. And it's occurring at above 6. If we can use that kind of like that compromise pH around 5.8, 5.9, we can get a little bit of both. So the charge neutralization, it's kind of like the individual assassin, and the sweep flocculation is kind of like the blob. It captures everything in its path. So we did talk about how alum forms aluminum hydroxide. It therefore uses up alkalinity in the water. And we can estimate how much alkalinity will be taken up by this kind of rule of thumb here. For every milligram per liter of alum, it requires about a half a milligram per liter of alkalinity. And we're measuring alkalinity as calcium carbonate. So if we need to add alkalinity because we don't have enough alkalinity existing in the water, we could add some different types of chemicals, such as calcium hydroxide. The reason we'd want to do that is we don't want to have a pH drop. If we, for example, we had 20 milligrams of, per liter of alkalinity in the water, and we were going to use up all of that alkalinity in coagulation, we could have some terrible pH drops, and actually it would make the water corrosive downstream, but also it would disrupt the coagulation process. In fact, we could have the coagulation process going the opposite way, and instead of forming floc, it would cause particles to become dissolved and repel each other. So chemicals that we might use to decrease the pH would include things like sulfuric acid. That's the most common acid that's used to lower pH. Hydrochloric acid is also something that can be used. And even carbon dioxide can be injected into the water, and it will form carbonic acid. So carbon dioxide bubbled into the water can also lower the pH. I'm going to give you an example of how the how the pH, excuse me, and alkalinity would figure into our treatment planning. So we have a water that has a pH of 7.2, and it has an alkalinity of 30 milligrams per liter, which is pretty low. That's a low alkalinity. And so we do some jar testing, and we find out that we need to have an alum dose of around 40 milligrams per liter, and that the best removal is at a pH of 5.8. So we have a couple different things we need to do here. First of all, we need to see how much alkalinity is going to be used up by this dose of 40 milligrams per liter. And if you remember, we said about a half a milligram per liter of alkalinity will be used up for every 1 milligram per liter of alum. So if someone in the chat could estimate how much alkalinity is going to be used up here. Let me look at the chat if I can find it here. Okay, I see the answers coming in. 20 milligrams per liter of alkalinity will be used up. That's exactly right. We just take our 40, and this is a rule, kind of a rule of thumb, but 40 milligrams per liter times 0.5 means we're going to have 20 milligrams per liter of alkalinity used up. So how much is remaining? Only 10 milligrams per liter remaining. That's probably too low. That would be scarily low. We could have some pH drops, and we could have some real problems downstream in the distribution system if we have an alkalinity that low. So we'd probably need to add some alkalinity, some calcium carbonate of in some form. So we'd probably add calcium hydroxide as our chemical here to increase the alkalinity. We also would like to lower the pH here. Where our pH is 7.2, and for our ideal coagulation, we'd like our pH to be closer to 5.8. So we'd have to also add sulfuric acid. And hence, we also see the problem that we can get into with using alum. So here we are having to add calcium hydroxide and sulfuric acid. That's a lot of additional chemicals to add, which may or may not be cost effective compared to just using some other type of coagulant or doing something like adding a polymer that might improve the removal without having to do all this adjustment, or a coagulant that doesn't use as much alkalinity. So we're kind of doing two things here. If you notice, we're walking through what a treatment scenario would be with adjusting alkalinity and pH, but also looking at some of the reasons we might not want to use alum. And so if you made adjustments like this, you'd want to confirm them by doing some jar testing. And we'll look at jar testing in a little bit here, and then monitoring it closely. We could consider other types of coagulants that work better at the given pH and alkalinity. And we could also think about just adding a polymer so that our alum dose maybe doesn't have to be as high. So those are all things we could think about. It can get fairly complex. I see a chat message come in here. Let me just take a quick look. Okay. One of those options could be that PAC here. Now that at PAC, it's already been pre-hydrolyzed, which means it doesn't have to take alkalinity from the water. So it's already had its chance to take up all of the hydroxide ions that it needs. And so we can also depend on this to, as soon as we add it, that alkalinity step doesn't have to take place. It can begin working to cause small particles to clump together right away. And we can create a pretty high quality flock, and it works over a larger pH range than alum. It has much less effect on alkalinity, if any, and it can improve the removal of those small organic colloidal particles. So this is an alternative. And once again, compared to alum, alum has to first form the aluminum hydroxide, and with the PAC, it's already formed. So some of the reasons we might not want to use alum is if we have water with very low alkalinity to begin with, and the pH isn't ideal. I'm not saying you would always do that. It might still be worth it to adjust the pH and the alkalinity, but it's a factor that you'd want to do a cost benefit analysis of. Also, alum produces a lot of sludge, and so you might want to have a coagulant that produces a sludge that's a little bit easier to handle and dewater. If you needed to reduce something like phosphorus, or some kind of a chemical, the alum wouldn't be as effective as the iron-based coagulants. And the iron-based coagulants, they're often used in place of alum for all these above reasons. They work across a wider range of pH and produce a denser sludge and so forth. However, they can cause problems with corrosion. The other little missing factor in here is polymers. Polymers could actually make alum more effective, and any of the coagulants more effective. Sometimes polymers can even be used as a coagulant. The polymers can be positively charged, negatively charged, or neutral with a variety of positive and negative charges. The downstream effects of the coagulant also need to be considered. And I'll give you a little example here. The ferric chloride, it is very effective at removing organic particles, and it produces a dense flock. It settles quickly. It works in cold weather. Flint used it. It was part of the reason why they had so much corrosion problems, because it's also corrosive. In Flint, they were looking to better comply with the disinfection byproducts rule, and ferric chloride was known as a coagulant of choice to remove naturally occurring organic matter, and it works in cold water. It just seems ideal, except for the fact that the additional chloride can make the water corrosive, especially in the situation of Flint, where they already had a chloride to sulfide mass ratio because of the raw water quality of the Flint River. And so this just added to the corrosiveness of the water. And you probably know the rest of the story. They had a lot of problems with corrosion of lead and metal pipes, and using up all of the chlorine residual. And so um, when we look back at some of these case studies, uh, these are good learning lessons for us. Um, just like what some of the big waterborne disease outbreaks. You had operators that were operating plants and were hoping that the water would be safe, and but things do happen. In the case of Milwaukee and Flint, these are lessons to be learned. So we want to look downstream of what the effect of our treated water will be on the distribution system. Polymers, I've mentioned that a couple times. They're basically large repeating molecules. They're long chains of these repeating patterns that have a variety of points where particles can attach. And so they can help to take your little microflocks, those particles that were destabilized, the negative particles that joined with a positive coagulant uh, atom or ion to form a microflock. They can begin to attach those to create macroflocks, larger flocks that have greater density and can be filtered and can settle out. And the use of polymers can make the coagulation process more effective, and you can often reduce your coagulant dosage, and you can work across a wider pH range. So that would require some jar testing to tune that in so it's working perfectly for your plant, but would be worth it. There's some different problems we can have with coagulation. We can have the flock is too small, we're not getting enough turbidity removal. If the dose is too low, if it's too high, we can have excess sludge, um, and we can actually get our positive charges so high that it causes the particles to re-stabilize. In other words, it's the opposite of forming flock. So we want to have just the right dose. We want to have the the proportion of negative and positive to be pretty close to neutral and a little bit on the negative side. If the pH is not in the right range, it can affect the flock formation. And if we don't have enough alkalinity, the coagulation process can use up our alkalinity and result in some corrosive water or some pH drops that actually affects the coagulation process. And this brings us to the topic of zeta potential. Zeta potential is measuring the electrical charge over all of the water. And if you see right here, the target zeta potential is around -4 to a -1 to -4, where if we had a lot of positively charged chemical, we'd get to the maximum that would be acceptable between 0 and +3, where you would think that if you had that maximum, it would be ideal, but actually just a little bit negative. So the negative particles are a little bit more predominant, and that range right there, it actually uh, promotes particles bridging together and connecting together, and also keeps you from overdosing if you run in that range. And so basically at the zeta potential, there's a electrode that detects the movement of particles toward the electrode, the positive electrode, or toward the negative electrode, and it measures the speed of the movement of the particles toward either electrode. That's the zeta potential. So it's a very complex little measurement, but running a little bit on the negative side is the best. And if you have a way to monitor the charge, like a streaming current meter or to take a zeta potential, it can help you to make some decisions in your coagulant dosage kind of proactively. So if you see starting to get a little bit too negative or a little bit too positive, you can adjust to that the dosage before it gets out of hand. We're going to go to pull 4 now, and the pull 4 is a question about zeta potential. Did I put you all to sleep? We have 72% here. We'll give another 20 seconds here. All right, we're gonna end the poll here and we'll share the results. And most of you, 64% said we would need to reduce the coagulant dosage. And this is kind of a conceptual problem here. And that zeta potential reading of +5 means we have more positive charges than negative charges. Means we have probably a little bit too much coagulant. So we'd most likely reduce the coagulant dosage a little bit. Remember, the particles in the water are negative and the coagulant is positive. And we looked at this little chart here where we like to run between about -1 and -4. There's some different factors that can affect the dosage, the pH that we talked about, the alkalinity, and the turbidity, of course. If you have higher turbidity, would likely have a higher coagulant dose. And so we need to perform some jar tests with different ranges of dosages. Colder water can actually create slower coagulation. So we might have to have a higher dose or more mixing. And the mixing energy makes a big difference. We want to have a lot of energy in the rapid mixing, but then we have to ease it off during flocculation so that we don't damage the floc particles. They're continuing to be suspended. And when we're calculating dosage, well, there can be different methods to do it depending on what the chemical is. We might have a dry chemical feed in pounds per day, a liquid chemical feed in pounds per day, and we need to know the chemical strength. Daryl showed us some calculations for disinfection, and he'll show you some more tomorrow using the pounds formula. The flow times the dosage times the weight of water equals the pounds per day. And if we needed to convert to gallons, we could divide by the weight per gallon. And we might have a little bit simpler situation here where we can determine how many gallons. I'll show you an example here. We have a plant flow of 2 mgd, and we need a liquid alum dosage of 12.5 milligrams per liter. So we can calculate the pounds of alum that we need with the pounds formula. 2 mgd times 12.5 milligrams per liter times 8.34. But there's an additional piece of information here. We have this aluminum solution. It's not 100%. It actually contains 5.48 pounds of alum per gallon of this solution, the alum solution. So there's two steps here. We can use our pounds formula, 2 times 12.5 milligrams per liter times 8.34. It shows we need a feed rate of 208.5 pounds per day of alum. And then if we just simply divide by the weight of alum that's contained in each gallon, we find that we take that 208.5 pounds per day and divide it by 5.48 pounds per gallon. The pounds cancel out, and we're left with 38.05 gallons per day. That's a pretty simple one. As we go to flocculation, you can see the flash mix is where we have coagulation, and then we go into the flocculation basin. We have a higher mixing rate, and then we ease off to medium and then a low mixing rate. And we're trying to keep the particles all suspended. We don't want them to settle out, but we don't want to agitate them to the point where they are damaged. And there are some good standards in the 10 state standards. There's some very specific standards about the tip the velocity of the tip of the mixing unit. You can see the higher energy and then the lower energy as your flock particles are larger and maybe a little bit more fragile. You don't want them to break apart because they're just held together with those little surface charges. A common mixer might be a mechanical mixer that has a vertical shaft, but there can also be horizontal mixers here where they're kind of like paddles. But it's the same scenario where you have intense mixing and then more and more gentle mixing. And you have to also be aware of the basin itself because there could be dead spots in the basin. And so you have to make sure that there's complete mixing. And you notice there's some baffling on the left of that image. You see some perforated baffle walls. So the water just can't flow in any path it takes. It has to flow through some baffles so that the flow is directed. And here's an actual image of on the upper right of your screen of a horizontal paddle that's installed in a flocculation basin. And then we go on to sedimentation. After flocculation, we've created some larger flock that's ready to settle out now. And so we're trying to have these particles settle out with gravity. We don't have very small particles anymore that will take 200 years to settle. We have larger particles because we've grown the flock. It sounds like a sheep herder statement. We've grown the flock, but FLOC, flock. We've created larger flock with higher density. So when we enter sedimentation, we have a reduced velocity where the water is almost standing still, and there's no velocity currents to carry those particles along, and they can now make their descent to the bottom of the sedimentation basin and settle as sludge. Here's a rectangular basin here. And the effluent weir, you can see the water coming in. If you can see it, it's kind of faint, but there's little flock particles that are in that water and they're settling out. Some are not settling till the very end. Those are the smallest particles. And at the bottom, there'll be some kind of a sludge removal device. So you can see there's some different zones that we can think about in the sedimentation basin. The quiescent zone is the quiet zone that allows settling to occur. As the water comes in, it's baffled through some inlets. And in this case, it's flowing upward through some additional tube settlers here that will increase the efficiency. We'll talk about that a little bit more, I think tomorrow or later on today. There you have the baffled inlet zone, the settling zone or the quiescent zone, and the sludge zone is the bottom where the sludge solids settle to the bottom and they can be removed. And then the outlet zone has to be a very gentle flow. You wouldn't want a high velocity flow in the outlet zone because it could cause particles to be dragged out with the velocity currents. Sedimentation basins are often circular, and in this case, the flow comes to the middle and it flows radially from the center to the outside weir, which is the circumference, the outside circumference of the circle. And there's a rotating rake that rotates circularly or radially around the bottom to push the sludge particles to the sludge hopper and to the sludge removal pump. And sedimentation typically removes up to 80% of all the turbidity. So you've grown those particles large enough where they can settle out, and most of them are being removed in the sedimentation. And it depends a lot on the types of solids, but especially on the preceding coagulation flocculation process. So if you're getting poor settling, the first place to look is at the coagulation flocculation process, the speed and intensity of mixing, the dosage of coagulation chemicals and polymers. And of course, it depends on the design of the basin too. The basin has to be large enough to allow time for the smallest particles to settle. The outlet will often have a V-notch weir where it will strain out anything that might be floating on the water, and you can actually use it as a way to measure the amount of water flow. If you look at this little image here, you can see if if the water is low in the notch, it can indicate you have a lower water flow, and if they're higher, it means you have a higher flow. And here's a little diagram. You can see the kind of a diagram from the top and from the side, how the water is entering into the center and flowing radially outward. The distance between the center of that sedimentation basin and the effluent uh, channel on the outside perimeter, if you look at that upper left image, that is the time that during which particles can settle. So if a particle takes 20 minutes to settle, we need to make sure that that distance, that travel of the water from the center of that sedimentation basin to the effluent weir is at least 20 minutes or greater, or that particle is not going to settle. And here's the same thing with a rectangular basin here, and that the particles need to settle between the inlet zone and the outlet zone, and we need to know how much time that is. So we're going to look at some calculations. Of the calculation that pertains most to the time allowed for particles to settle is called the overflow rate. And we'll look at that in a second. And here's one more image here of a sedimentation basin, and you can see the sludge scraper arm at the bottom, and it rotates very slowly to push sludge toward the sludge hopper. And you can see the inlet right in the middle on the bottom that's coming up through, and the water is being evenly dispersed. And it begins its travel from the center radially toward the outside, towards the outlet trough. So small particles are going to have slower settling velocities, and so if you want to remove those very small particles, you have to give them enough time to settle. And so we do the overflow rate for this purpose. And if you were to look at uh, a particle as it's flowing from the center toward the outlet here, if we had the smallest particle that would settle here, it would just barely settle before it reaches the outlet. If we had a particle that was smaller than the basin could handle, it wouldn't make it. It wouldn't settle before the water goes out. So that has to do with the overflow rate. And I'll show you a particle here, an example of a particle. We have a 10-foot deep sedimentation basin, and we have this very small particle, and it settles at a rate of 0.013 feet per second. So how much total time would be required for the particle to settle through that 10 feet of water? We can take the 10 feet of water, that's the depth, divided by the speed of this particle, divided by 0.013 feet per second, and we get 769.2 seconds. That's how long it would take that particular particle to settle. So we need, let's convert this to minutes first. We'll divide that 79.2 seconds by 60 seconds per minute. That means this particle requires 12.82 minutes to settle. So we need to make sure that our overflow rate gives us a time of travel that's larger than that. And usually most sedimentation basins would, but as you imagine that water traveling from the center of the sedimentation basin to the outside rim, in this case, it would need to be greater than 12.82 minutes in order for it to settle. Here's a couple of other images here of those particles that have settled at the bottom as sludge, and we're collecting them as sludge at the bottom and sending them to be taken to a drying bed or incinerated or to a landfill. So overflow rate. Generally, the overflow rate, it compares the flow of the plant in gallons per day or or 1 million gallons per day, and it is compared to the area. So we're taking the flow in gallons per day or gallons per minute and dividing it by the area in square feet. And so generally the overflow rate we're looking for is somewhere between 1 and 1.4 gallons per minute per square foot. And so if we look at a calculation for this here, we take the flow in gallons per minute and we divide it by the area in square foot. So I'll show you how we do one of these here. We have a cylindrical sedimentation basin, and it has a diameter of 50 feet, and the plant flow is 2,100 gallons per minute. So we want to know what the overflow rate is. I'll make a little diagram here. It's always good to draw a diagram of your when you're doing a math problem. And here's our equation, like Daryl showed us, area 50 times 50 times 0.785 gives us 1,962.5 square feet. That's the area, surface area of the sedimentation basin. And we take the flow, that should say 2,100, but I rounded it to 2,000 gallons per minute, divided by 1,962.5, and our overflow rate is about 1, or one, just a little bit over 1. So it's in the right range, 1.002 in this case. So that overflow rate, that's related to that, directly related to that settling time of particles. And if you think about, if you look at that overflow rate, where I have the 2,000 gallons per minute divided by the 1,962.5 feet, that gallons per minute, you could actually express that as cubic feet per minute, which would be like a foot to the third per minute. And if you took the foot to the third and the square foot at the bottom, what you end up with is foot per minute. So it's actually a velocity if you express it like that. Detention time is how long the water remains in the basin. It's based on the volume. So detention time is the volume divided by the flow. And this is also important. The detention time for sedimentation basins ranges normally between 3 and 4 hours. If you had a situation where you had a lot smaller particles, maybe there's a surface water that it's difficult to remove the very small particles, a larger sedimentation basin would actually help with more a larger overflow rate with a larger area, and also greater volume to give you a longer detention time, more on the 4+ hours. So it has a big effect, the size and area of the sedimentation basin. But detention time is just simply the volume divided by the flow. And here's an example. We have a cylindrical sedimentation basin again. It has the same diameter, but this time we have the depth. And the plant flow is 800 gallons per minute. What is the detention time? Here's our diagram again. But our equation includes the depth this time. Just like Daryl showed us, the volume 50, that's the diameter, times 50 feet, times 0.785 times the depth of 10 feet, times 7.48 gallons per cubic foot, and we get 146,795 gallons, 146,795 gallons. If we divide that by the flow of 800 gallons per minute, we'll get our detention time, 183.5 minutes. If we divide that by 60, we see that is right in the ballpark of what we were recommending at the top there, just a little over 3 hours, 3.05 hours. And one last additional equation is the Weir overflow rate, and that is the flow in gallons per day per feet of weir length. And in general, we don't want it to go over 20,000 gallons per day per foot. In in a rectangular basin, the weir will be a linear. In a cylindrical basin, that the weir will be the circumference of the sedimentation basin. In other words, it's around the outside of the sedimentation basin. So this particular one, again, it has a diameter of 50 foot, and the flow is 2,100 gallons per minute. And the weir is the perimeter of the basin. So if we want to calculate the weir, we're going to have to use the diameter. And the formula for circumference is diameter times pi. So if we take pi, I'm just rounding it off to 3.14 times 50 feet, we can see the length of our weir is 157 feet. And if we want to know our flow in gallons per day, we'll take that 2,100 gallons per minute and times it by 1,440 minutes in a day. 1,440 is 24 hours in a day, 60 minutes in an hour. 24 times 60 is 1,440. So 2,100 gallons per minute times 1,440 gives us 3,000,000 and 3,024,000 gallons per day. So now we can finally do our weir rate, where we take the gallons per day divided by the length of the weir, 157 feet, and we get 19,261 gallons per day per foot. So that should not exceed 20,000, and it doesn't. It is, however, on the high end of the range. So if we started producing a lot greater flow of water with this treatment plant, we could exceed the capacity of the detention basin. And the weir overflow rate really pertains to the velocity, the current velocity of the currents flowing out. So if you start disturbing the water, you could disturb that quiescent area and start having velocity currents that could cause you some problems. And now we're going to go to pole 5. Get out your calculators, and we're going to do a overflow rate, and we can probably give 2 minutes for this. If Scott is still available to set the timer, that would be great. But we'll give 2 minutes for this one. Give another 30 seconds here. How many of you would like more time to work this out, or would you like to see the solution revealed? Let me see in the chat. Oh, somebody said the option to answer the poll went away. All right. All right. I see Cynthia says 1 more minute. We'll do that. And I see some people say, so if I figured if even one more person wants a minute, right? So let's do that. 1 more minute. Hey, Scott, did I do something to make the poll go away, or is it still there?
That I'm not sure. It should still be there. It's still open.
For some reason, I don't see it on my screen, but it's not necessary for me to see it. 5 seconds. Okay. We're gonna show the solution now. Can you see the results, Scott? For some reason I did something. I lost my ability to see it. So 43% said 1.1, and 25% said 1.3. So now we're gonna see how well I explain this concept here. Yes, yeah, you will get credit. So the first thing we need to do is convert the flow to gallons per minute, because in this case, we're looking for the overflow rate in gallons per minute per square foot. So we take that gallons per day and divide it by 1,440 minutes to get it to 3,650 gallons per minute. And then we have to calculate the area of the sedimentation basin, diameter squared times 0.785, 3,316.6 square feet. And now we have everything we need to calculate the overflow rate. The flow in gallons per minute divided by the area in square feet gives us 1.10 or 1.1 gallon per minute per square foot. Answer A. Does that make sense to everyone? So there was an additional thing that I kind of threw at you there where you had to convert back from gallons per day to gallons per minute. Now, infiltration here, we have some media. You can see the coal anthracite at the top, the sand in the middle, and the garnet at the bottom. That's a multimedia filter. Sorry. And the water comes down through from into the top, goes through the filter, and it's collected at the bottom. In those perforated pipes there, that's the underdrain system, and it goes on to the clear well to be disinfected. Those little wash troughs there at the top, that's to capture when the water reverses flow and there's backwash, the water goes from the clean water up through the filter. It expands the media and cleans it, and the wash troughs collect that dirty water, those particles that were trapped and clogging the filter, and they go to the backwash basin. So the way media is layered, normally the coarser media with the lower density is on top and the finer media with the higher density is on the bottom. There's a couple reasons for that. It helps to expand the ability of the filter to, if you had the fine media at the top, it would just clog up and you'd have to backwash the filter more often. But if you have the coarser media on top, it can collect the larger particles and the finer media can collect the smaller particles and your filter run can continue. But also when you backwash and all the media is expanded and suspended, it will drop back into its place depending on its density and size. And there's a little period when you first start filtering. There'll be a period where you first filter, the turbidity will be high because it has not yet become coated with coagulant chemicals. The filter media needs to be coated with some of those coagulant chemicals so that it can remove the smallest particles through what they call adsorption. So you have two mechanisms. There's the physical straining of particles trying to get between the grains of media, and there's also adsorption where the particles stick to the media. And here's you can have a single media, just sand, all the way to a multimedia, which is a normal orientation of anthracite coal, filtration sand, and garnet. And just like I explained, it can improve and extend the filter runs because the larger particles being captured at the top and the smallest particles that make it all the way through are captured with the smaller layers. So you have the anthracite, the sand, and the bottom layer. And the single media filters, they tend to that like that one on the far left, most of its filtration would happen in the first couple inches or a couple centimeters even, and it would become clogged, and you wouldn't really be able to effectively use the entire volume of that sand. And you can see the densities here of the garnet and the sand and the anthracite. The garnet has a much higher density than the anthracite, and these are ordered by density. They're exactly the opposite of the way they're stacked in the filter. And here's an example of the basic two mechanisms here. In physical straining, the flock particles just can't get between the particles. They can't fit between the particles of media. With adsorption, the particles are adhering to the media. They're electrical or electrostatic charges because of that coating with the coagulant chemical. Those little negatively charged portions of the flock particles adhere to the positively charged coagulant. There is some design considerations based on the size of the media and the depth of the bed. Here we see an image on the upper right of your screen of some sand media, and its size is its effective size or average size is about 0.5 millimeter in diameter. And so a bed depth to media diameter ratio of right around 1200 is what they often shoot for. And so I'll give you an example here. We're using this 5 millimeter sand here for one of our media layers, and the depth of that layer is 24 inches. What is the L to D ratio? First of all, to do this, we would take that 24 inches and convert it to millimeters because our particle is 0.5 millimeters. So if we take that 24 inches times 25.4 millimeters per inch, we get about 609.6 millimeters. And if we take that 609.6 millimeters, that's our L, and divide it by the diameter of the particle, 0.5, we get about 1219.2, which is real close to that preferred LD ratio. That's part of just a little segue into how the media layers might be designed. In filter ripening, you notice this is a graph of turbidity. When we first start a filter run, there's a the turbidity spike. You see, we start out, it's as high as a 1. We want it to be below 0.3 NTU. And so that spike is, we've just gotten through backwashing our filter, and we need a little period for that media to become coated with coagulant chemicals. So this is called filter ripening. And eventually we will get to the point at the end of the filter run, and this particular filter is run 40 hours. At the end of that filter run, we start getting the turbidity increasing. We're getting what they call breakthrough. Turbidity is making it through the filter, and we stop the filter run. And during this little ripening period, we probably will want to run that filter to waste until the turbidity gets within the operating range. The filtration rate is important too. The filtration rate for a rapid gravity sand filter could range between from all the way from 2 to 10 gallons per minute, but normally we're wanting to run these things between about 4 and 6 gallons per minute per square foot. So the water is coming down to the top of the filter and it's flowing through. That you see that supernatant water on the top. Eventually, as the filter becomes clogged, that water on top will get deeper because it can't make it through the filter as fast, and so we're having some what they would call head loss. The weight of the water is not able to overcome the clogging of the filter. And so we in normal, when you have filtered water, it's coming down through the media and out the filtered water outlet, and it's going to the disinfection basin. And when we backwash, we close that filtered water outlet and we have clean backwash water coming in, and it's going up through the filter to backwash it. You can also have the same kind of media in a pressure filter. And instead of backwashing by the head loss, we could backwash according to the pressure differential between the incoming water and the outgoing water. And you see this has the same layers, the anthracite, the sand, and the garnet, and an underdrain system that collects the cleaned water and also acts as a way to transmit the backwash water up through the filter. So in backwash, you're basically reversing the direction of flow and you're fluidizing the media. You're expanding the media between 20 and 50% so that the particles are separated from each other and water can flow between the particles and get rid of the contaminants that are trapped in the filter. And then after you're done backwashing, the flow is stopped, the media settles back into place, and you can begin filtering. Backwash rates are higher, generally in 15 to 20 gallons per minute per square foot, because you want to lift and expand that media. And you have to be careful. If the water temperature gets colder, the water is denser and you could actually lose some media through backwash if you don't decrease the backwash rate. And you have to know the kind of media that you're using. If you have a really dense media, you might have to have higher filtration rates. And if the filtration rate is too low, you can actually accumulate contaminants in the filter media, and you get things what they call mud balls, globs of contaminants. And if the filter is allowed to be have insufficient backwash over a long time, it can actually be kind of like it can be kind of turned to a solid kind of a mass, and you can get these cracks. It's like cracks in the mud balls, kind of like a crack that can allow untreated water to pass through a channel in the filter. And so you want to make sure that you're backwashing sufficiently, whereas too high is associated with media loss. So if we have a filtration rate problem here, we have a gravity filter that's 10 by 20 feet and has an inflow of 1,000 gallons per minute. What's the filtration rate? We look at the area. 10 by 20 is 200 square foot. And we take the 1,000 gallons per minute, divide it by 200 square foot, and we see our filtration rate is right in the ballpark, 5 gallons per minute per square foot. And if we wanted to backwash here, we have the same size of the filter, 10 by 20. What would be the flow needed to attain a filtration rate of 15 gallons per minute? Well, we'd have to divide the flow by that area, and it would have to equal 15 gallons per minute per foot. If we multiply both sides of that equation by 200, we have 200 square feet times 15 gallons per minute per square foot. That's our minimum filtration rate that we want. We'd need a flow of 3,000 gallons per minute. Because when you're actually applying the filtration, the backwash, you're going to be adding be sending a certain flow rate to that filter. So we'll do our last poll of the day here. And we have a gravity filter. It is 15 foot wide and 25 feet long and has an inflow of 1,200 gallons per minute. What is the filtration rate in gallons per minute per square foot? We're almost up to 70% here, and we're a little over time. I'm sorry, I'm slow. And we'll open it up for questions, and I'll ask if Daryl could come back on, and any questions that that we can answer today, we'll be glad to do that. And we'll have another chance tomorrow to answer some more questions. If we have any questions in the queue, Scott, you can let us know. And I'll go ahead and I'll end this poll for now. I'm sorry if some of you are still struggling on it, just for time's sake today. Most of us said 3.2 gallons per minute per square foot. And the solution here, we multiplied 15 feet times 25 feet to get our filter surface area, 375 square feet. And we took our 1,200 gallons per minute divided by 375, and we got a filtration rate of 3.2 gallons per minute per square foot. Great job, everyone. And we're open for questions.
So Greg, just to clarify something, the poll number 5, there was the actual initial poll question had circumference on it, and then the subsequent slides, so that would be slide number 90. We gave it in circumference we were asking for, and then the subsequent slides mentioned diameter. So I think that caused some confusion.
Oh, yes, yes.
So I think that unfortunately there were people who were probably converting from circumference to diameter, and that's likely why it took people quite a while to get through that, and then there was some confusion. So
So I made a typo there. Yep. Sorry about that, everyone. Thanks for pointing that out, Daryl.
well, I just wanted to make sure it was clear for people who had questions.
Yeah, that's a good one. Yeah. Well, we need to get these our audience an instructor that is not so scatterbrained.
Oh, you're doing a great job, Greg. There was one little thing, unfortunately, probably. I could see why it might cause some frustration.
Well, if we don't have any questions coming in, I'm not sure how to interpret that. If we explained everything so incredibly well that you can't think of anything that was unanswered, or it was so poorly presented that you can't come up with a question. You don't know what to make
Greg,
of it.
there was one question.
Okay.
It was probably around slide 90, around that. Uh,
Ingrid, you ended up got muted there. I'm not sure what happened.
the question was, what about gravity filters with GAC?
Oh, yes, it's a good question. We're going to talk about that a little bit tomorrow. But there's two places where where GAC will be used, and GAC means granular activated carbon. The first place where that might be used is before coagulation even occurs, and oftentimes it won't be granular. It will be powdered activated carbon that's added before coagulations to remove taste and odor compounds before. And another place where the granular activated carbon is used, it's often used as a separate filter, completely filled with granular activated carbon after sand filtration. And that's often done as a polishing step to it's strong in adsorption to remove natural organic matter and personal care products after filtration. Sometimes granular activated carbon can be added as an immediate layer in a sand filter. The only problem, the only caveat with granular activated carbon is it's not going to be something that can be backwashed forever. I mean, you would still backwash the filter, but the granular activated carbon would have to be replaced at some point. So therefore it makes more sense actually to have it as a separate unit as a polishing step after sand filtration. Great question.
Hey, Greg, there's a question regarding the remainder of the slides from today.
Don't ask that question.
I didn't ask it.
No, I'll fit them in tomorrow.
Okay.
Yeah.
Thanks.
Yeah, we have a couple slides about turbidity measurement, and we'll just fit them in tomorrow. About turbidity. Appreciated you all being here. The second day and time, Cynthia, it's same time and same link. Is that correct? Scott, Daryl, and Ingrid, same link?
Yes, it'll be the same link as today.
All right, Greg, I'm thinking that if we'll hang out for a couple more minutes, but to see if there's any more questions, but we should probably let people get going. Does that sound good?
Sounds good to me. Thank you
All
for
right.
all your great questions and participation. And I think I kind of jammed you a little bit on some of the math problems. You know, with these presentations to cover all this stuff, they can tend to get kind of long and it can limit the time you have to work on a problem. So sorry about that. But we'll try to give as much time tomorrow. And bring your questions tomorrow. Bring your hardest questions first, because Daryl's going to be presenting first tomorrow. And save the easy ones for me at the end.
All right.
Well, thanks, everyone. We have quite a few folks logging off. So I think we're going to call it for today. So we'll see everybody tomorrow. Again, same Zoom link and same time. Thanks again.